hello everybody. Sorry I cannot make the presentation in your speech, in your language, because I forgot the vocabulary. I used to speak years ago. I've got a girlfriend from Venezuela, so I had to, but nowadays I just knew just a few words, a poquito. So, but that's why I will speak English. So, but when you've got questions, when you something do not understand, then we have got, my colleagues can translate this to your language, okay? So thank you for coming here along. Okay, we are a little bit late because there was some confusing regarding the room number, sorry about this. But now everything is fine, you are here. And now will hear something about a very extravagant technology of ZEISS. It's the helium-ion microscopy. And I will show you the technique of this and later some examples. So it's very easy, you don't have to write some notes or something like this. I think we can also provide you some information material of this technique. So we'll start with some overview of the ZEISS product portfolio. So you see here on the left side the 2D imaging tools, so light microscopes, super resolution microscopes, and so on. And here's the 3D imaging tools, and it goes down from the macromundo to the micromundo. So you see here the resolution goes from microns down to sub-angstrom with a TEM. And you see here the helium-ion microscope is just placed between the scanning electron microscope, so the SEM, and the TEM, the transmission electron microscope. I would suggest to use this, the name not like a helium-ion microscope, I would call this scanning ion microscope, but I think the aberration of the SEM, the SIM, or SIMS, is already occupied by the secondary ion mass spectroscopy. So that's what we call this helium ion microscope. So there's a new technique by ZEISS. ZEISS acquired last year the company X-Radia. They produce X-ray microscopes. So they are placed just between the LM, so the light microscopes, and the electron microscope. So they close really the gap between the light microscopy and the electron microscopy. And if you are interested, later on I can show you something about this technology. So we have got enough time, so I can show this when you are interested. So, but now we'll start with the helium-ion microscope, and I will show you how you obtain this kind of images, for example. So this is some catalyst grown on nanowires, and I will show you the technique behind to get this high-resolution surface imaging, this large depth of focus inside the images or the sample, and there's no charging of the sample, so you don't have to coat your samples. Later on I will show you experiments of nanofabrication, because you can also use the helium or the neon or the gallium to make some nanofabrication of your samples. You can deposit material, you can etch, you can let grow pillars on your samples, or later on you can also prepare TEM lamellas. So this is my outline. I will start with the technology and principle of the source. So this is the really secret of the microscope, and it's very, very easy to understand. You don't have to be afraid, so it's very easy. Later I will show you application images and, fabrication images. So everything starts in the 19th century as the people start using photons to use it as a microscopy, a particle wave, or for the microscopy. And in the late of the 1960s, they start to use the photons for modification of material. Then the electrons, they were used in the 1930s for the microscopy. Then the electron microscopy starts. And for the magnification, what's used 50 years later. So for the ions, it's vice versa. So they were first used for modification in the 80s. And later, in the 21st century, we started to use it for the microscopy. And this has got a lot of advantages in the microscopy. And some customer told me that the ions are the electron of the 21st century. So the principle is based on the field ion microscope invented by Erwin Müller in the 50s. And the principle is very simple. So first we have got the chamber, it's evacuated, so there's nothing inside, a vacuum. And you've got a cool tip. Usually we use tungsten, sorry. Then you have got a high voltage between the tip and, in this case, the screen. Then you've got gas. Okay, we use helium. And in the front of the tip, the gas will be ionized and will be attracted to the screen, and that's because it's a viewing screen that will cause an image, and you can record this image with a camera. And this is how the first image of Erwin Müller looked like. And yeah, there you see a lot of points inside the image. And you have now to interpret these images. And actually, Erwin Müller was really the first person who really saw directly atoms. And this is his experiment, for example, here. And he never received a Nobel Prize for this. So this is Erwin Müller with one of the, some model of his tip, the front of the tip. And he shows here all the the tungsten atoms of the tip. It's a single crystalline, but you can also use polycrystalline materials. But then the interpretation of the images makes no sense. So, but now I will lead you to the principle from the field ion microscope to the gas field ion source. So this is how our ion source is called. So this is now the blunt tip. So it's unsharpened. In cross section it looks like this. You see the atoms here, and each edge atom is a source for one single helium ion beam. You see there's a lot. And each ion beam will cause a point on this viewing screen. So this, you see all this, a lot of rings and a lot of points here. And this is because in our worlds, in the ZEISS world, it's an unsharpened tip. Our tip looks like this. So in the ideal case, we just would have one single atom in front of the tip. But this one single atom is not stable. It just flies away. Sometimes it's there, you see it, but just for seconds, and then it's flying away. But what is stable? It's the so-called trimer. So 3 single atoms in the front of the tip, and they will produce 3 single ion beams. And you see this here in the image. You don't see this very low intensity. The next neighbor atoms, you see this here, but what's important is these bright 3 spots here inside, and really this cause our source. And then we use an aperture and use one single of this. So in this case we have really an atomic sharp probe size. So now you ask, what's happened when this tip is broken? So it's blunted. So this is some physics now, okay, but not a lot. So you've got here now the extractor voltage and the emission current. And when we increase the extractor voltage, you see nothing. It has to be some standard word. Then you see a little bit of trimer inside. And there's a maximum and optimum where we see the brightest trimer. And this is what we use for the imaging, for example. And when you later on extractor voltage, it's increased, and they see the neighbor atoms. And later on, there's a point where the tip breaks away, and then you see this Erwin Müller image. You can't see with this right now because it's too bright here. But this we use to sharpen the tip inside the microscope automatically. So we really can automatically sharpen the tip inside the microscope. So the lifetime of one tip is just around 1 week. So it depends on your work. So when you do nothing, then it's of course longer. But we can sharpen this, and this takes some minutes. So there's an automatic procedure to do this. So when you compare the brightness and the probe size with other sources, for example, with the liquid metal ion source, this is used, for example, in the focus ion beam, cross beam, for example. They have got probe size with some nanometers. The Schottky field emitter is used in the FE, SEM, or the field emission scanning electron microscopes, or TEMs, transmission electron microscopes. It's sub-nanometer, and it's 2 magnitudes brighter. But with our helium ion microscope, we really have got the scanning probe with the highest brightness and the smallest probe size. And this, you see the probe size, it's specified by 0.35 nanometers, and it's better. So it's really atomic sharp probe size. So the only limitation is the movement of the tip. So the tip it's not allowed that the tip is moved. That's why it's cooled. And we cool this with solid nitrogen. Solid because when you've got liquid nitrogen, then it's bubbles. And this causes movements or vibration of the tip. So that's why we call this with solid nitrogen. So this is, I think, the second. Maybe there's another. It's a little bit more physics now. This is some optics now, because you have got, when you're using lenses inside the microscope, you have always the aberrations of the aperture and of the lenses and so on. So, and I will now show you for the normal, for the SEM or for the normal microscopy, what's limiting the probe size. So first, you've got here the sum of all the summons. First, you've got a demagnification summons. So you have to demagnify your source, the image of your source. So this is a constant. And you've got this spherical aberration. This goes with the power of 3. You see, this is the green line here. The green curve. This will also limit the probe size. Then you've got the chromatic aberration, so the different energies of the electrons. This is linear. This is the blue line here. And later on you've got a diffraction error. So this is caused because of the aperture, and this goes by the power of -1. So and this is the red one here, and this is the ugly one. Because the superposition of this means that here you have got really, you will obtain the smallest probe size. So that's why all the microscopes has to be corrected. You know, the chromatic correction or the spherical aberration, the correction and so on. This costs lots of money and so on, but this also reduces the probe size. So now the diffraction option. Now look at this. When we compare the wavelength of the electron beam and the helium beam, then it's, you know, the wave-particle dualism, you know this, then you see that the wavelength of the helium ion beam is 2 magnitudes smaller. So that means we can forget this diffraction error. So and that means when you see the superposition, we can really go to the smallest beam size, probe size, down to the smallest probe size. So that's why we can use this small probe size from 0.35 nanometers. So this source is now placed on top of the microscope. You see, this is a microscope. It looks like a SEM, normal SEM. That's also the control panel. Everything is like the SEM. So we just use helium. And the first devices were built only with helium. So this is the Orion series. The people started to use this device, of course, for imaging, but they learned very fast that you can also use the helium ion to make some nanofabrication. So they asked for a higher element. So we built the Orion Plus microscope. There you can use the helium and the neon as an imaging gas or for nanofabrication. So, and with the new Orion nanofab, we can combine the helium, neon, and additional the gallium. So this is a really powerful tool. It's like a Leatherman. Okay, you see again, high resolution. You can precisely measure your material, or you can rapid prototyping with gallium. I will show you later. This is more detailed. So again, this is an image of an electronic device, and I will show you now what's behind the technique to obtain this high lateral resolution images with a very high surface sensitivity, large depth of focus again, and again there's no charging. So you see the bright parts here, they are conductive, and the dark ones are non-conductive, but you don't have to coat your sample. And by the way, working distance just around 10 millimeters. So it's a very high, very big working distance in comparison with the SEM. So when you bought an SEM, you always make some resolution tests inside the SEM. And therefore you use a sample which is gold on carbon film, because there you've got a lot of contrast between the gold particles here and the carbon film, black. And then you see a sharp edge here, and then you can measure your contrast. But when you want to have a closer look to the surface, for example here for the gold particles, you have to reduce the energy, and then everything looks very blurred. So there is no sharp edges anymore here, but okay, you can see something on the surface of the gold particles. But now, attention, so this is the image in the helium ion microscope. There you see the gold particles, and on the gold particles you see a contamination of the carbon. So, and why is this so? So when we now compare the SEM, so the electron interaction with the sample and the helium interaction with the sample, then you see that the area of the surface interaction is much more bigger than with the helium ions. The excited volumes, you know this, they produce a lot of secondary electrons here in the lateral dimension, which is very smaller for the helium ions. So they penetrate deeper into the material, but the area of surface interaction is very small. So this will cause this high resolution of the surface. This is an example. This is some polymer, and it's non-conductive, and we didn't coat this. So, and there's a trick behind this, because of course the sample will be charged. So in the SEM, the sample depends on the electrons which go out and in. In SEM, the sample can be charged positively or negatively. In the helium ion microscope, the sample will be always charged positively, because electrons go out and positively ions go in. So that means after a while, your sample is oh sorry, it's negatively, oh no, it's always close. It's positively charged, sorry. It's positively charged, and therefore that's why the electrons cannot go out of the sample, so they will fly back. And after a while, every image will be black, because there's no electrons coming from the sample. So we have got an electron flood gun. So this is like an electron shower which blows low energy electrons above the, over the sample and after each scan. So that means the positively charged specimen will be neutralized by this electron flood gun. So now I'll show you some application images, and I start always with this life science application. So these are stereocilia inside the ear, inside the inner ear. So there's a cross section, and these are inside this. And when we hear, they move, and they will cause some current, and then we will recognize this as a tone, for example. And there, these stereocilia, some hairs, they are connected with these tipplings. And the people in the SEM world, they had really problems to make this visible inside the SEM images, because they have to coat their samples. And this coating causes that these tipplings will break, so they cannot see this. So this is an uncoated film, uncoated sample, and you see easily the tipplings between these stereocilia. This is a cell where viruses entering the cell. You see the virus, this one is outside and there's some inside. This is the cytoskeleton of the cell. And again, it's an uncoated sample. So it's very interesting, for example, for the life science imaging. This is a resist. You know that in the semiconductor fabrication you use resists which are no, I'm losing the which will be developed and so on, and then you have got the structure on your wafer. The resists cannot be made visible inside the SEM because of the charging artifacts. And in comparison, you see a clearly resist film here inside this helium ion microscope image. So this is an NBPT film. So this is a monolayer of nitrobiphenylthiol. I don't know what this is, so sorry about this. But you see, this area is exposed via E-beam lithography. So they make this structure inside. And due to this, because of this exposition, the chemical formula is changed from NO2 to NH2, and you see you can make this change of the formula, of the chemical formula, visible inside the helium ion microscope because of the different work functions of the material. So in comparison with an SEM, there you see nothing. Now, okay, fabrication images and examples. So the Arine nanofab is modularly expandable. So as I told you, we can use helium or neon as imaging of fabrication gases. Then we can use a gallium column. So this is a gallium. You can use gallium as a third gallium for milling, for example. Then you can use a gas injection system. This is for growing some pillars or etching of the sample. And this is, we can use an electron beam and an EDX detector to do analytics. Because right now we just can do imaging and fabrication, nanofabrication. So, nanofabrication. So this is a C lamella, or a C antenna. The customer produced, I think this is an aluminum. This is produced by a gallium ion beam FIP. And this was the smallest structure the customer could write with the gallium ion beams. So later on he wants to make some experiments. I think I show you the results of the experiments. Okay. But now compare this with the helium ion helium ions. So this is a structure, it's I think 5 or 10 times smaller we can write with the helium ions. So and the customer, they want to measure the phonon structure inside these antennas. So maybe you will ask for the defects at the edges when we write the structures inside the material. So this is a thin gold film. So it's so thin that we can just put it into the TM. So it's transparent for electrons inside the TM. And we make this double antenna, the structure here, with a 4 nanometer gap inside. So when you look, this is the same, this is the tip of one of this antenna. When you see, there's really minimal lateral damage. So this is a customer, I think this was IBM, and they want to produce such an, for the DNA sequencing, they want to produce this transistor. So this is a sandwich, so a multi-layer, and they want to produce 5 nanometers holes inside. And usually they use a TM, and this costs a lot of time. And they came to us with a lot of sample, and they were happy like this, as they went away from our demo center with everything was done, work of a year, because we just need some 15 seconds to drill a hole inside, where they, it's 400 times faster than in the TEM. And it was with a better accuracy, the holes. Graphene may be the future material because of its electric, optical, and thermal and mechanical properties. And I show you now some example of the nanoribbons. You know, graphene, carbon, and you can the band gap. You can increase the band gap when you decrease the width side of a nanoribbon. And therefore, we made an experiment. This is a monolayer of carbon here, and we try to reduce the width of the ribbon to its minimum, and we could produce 5 nanometer with small ribbons of the carbon. So for the future developments, it's very important to make everything smaller. Again, we can also do some ion lithography, and usually when you write with electrons, there is a minimum of distance you can write because of the so-called proximity effect. So you will destroy the last written line when you draw a line really near to the line before. But you can really decrease the distance between these lines by using helium ions. So this is an example for this gas injection system, where you use some gas which will be cracked and will produce this kind of pillars inside on your sample. And when you compare this gallium produced one with the size, with the width of 160 nanometer and the 36 nanometers here, just see that there's a different scale bar for this, and you can really reduce the overspray, and because of the lower proximity effects when using helium ions. So you can write your structures as you like. This is an example for using neon ions. So these are some aluminum pots, and there is some there you can cut with the neon. So it's, I always say it's I will show you the difference between the neon, helium, and gallium. Here you see this. So gallium, this is a gold film, and we machine away, we milled away this gallium here, this gold film, this area with gallium, and this it costs seconds. And then we use the neon for the fine structuring, and later on you can do the helium for the precision work, so you can really cut this cross inside this double bow tie. So later on you can combine all these three ions and prepare your, for example, your TEM lamella inside your helium ion microscope, like this example. So, and I think now I'm coming to the end, and you see again machining with helium ions, with neon ions, and you see the helium ions are here, so it's the same scale bar, and this is gallium. And I hope I could show you that the Orion nanofab is really a tool for imaging, of course, for nanostructuring and analysis in material and life science, for the ultra high resolution in surface imaging. Remember the probe size of 0.35 nanometers. We've got the charge neutralization for insulating samples, so there's no coating needed. And of course, we have got all the advantages in nanomodification due to the sub-nanometer probe size. Yeah, thank you for your attention.